In this video, we'll briefly discuss the relationships between current, voltage, and power and energy stored in a capacitor. So here's a capacitor. It has some current I running through it and a voltage VC across it. Its capacitance is C. We're familiar from previous videos that the current and voltage relationship is like this. Then, of course, we could combine them to get the power as the product of V times I, and plugging I in from above, we can write this. We could also get the voltage from the current like this. If we have some initial value of voltage at time t0, well, we just integrate from t0 to t. We need a 1 over c. And notice I'm using tau instead of t for the variable of integration because t is the limit here. So you can't have the limit be also the variable of integration. So that's just a change of variable, a dummy variable tau. Okay, so now we know what the current looks like if we know the voltage, or we know what the voltage looks like if we know the current. We have an expression for the power. You can integrate power to obtain the capacitor energy. So in this case, I'm just integrating from minus infinity to t. This, of course, is the same as 1 over c. So in my energy expression, that's already included. So we're not going to worry about that initial condition. Here we can perhaps assume that at time t equals infinity, there's zero energy stored. We can assume that at time t equals negative infinity, there's zero energy stored in the capacitor. So plugging this in from above, we have a c. We can factor it out, assuming that the c is constant. Then we recognize that this is a derivative, in fact. Oh, and for completeness, I want a VC here. Well, we know that the integral of a derivative of a function, and here's that function, is just this function itself. So this ends up being 1/2 from the function and then a c and a VC squared. Instantaneous energy stored in the capacitor. Okay, so we can look at an example. Here is a capacitor. I'm assuming that we've charged it as follows. At time 0, it has 0 voltage across it. Charge up to some value C0 at time t1, and then hold it, and then at time t2 we start discharging back down to 0, arriving at 0 at time t3. Okay, just some observations. Because we know we're interested in the time derivative of this, for the current, we can start thinking about the slope. Well, here the slope is 0. Let's call this m2, m1. The slope is v0 divided by t1. And then here the slope is m3, which is negative v0 divided by t3 minus t2. Okay, so now we can get the current, and completeness dictates that I will call that a V sub C. Let's call it V sub C. All right. So the current will start off at some value, constant, right? Constant slope. We'll go ahead and label this M1, 0, M3. And then after it's all over, nothing, right? Okay, this is our current. And then we can multiply these to get the power. So shrink that a little bit. So putting in our major times here. Well, our power looks like this. It starts right at time 0. One of these, right, voltage is 0, so power has to start at 0 because P equals VI. So it needs to start at 0, and then it's going to increase linearly because current is constant but voltage is linear. So where does it go? Well, it goes up to V0 times M1. M1 is just V0 over T1. So let's put here V0 squared T1. And then over the next segment, it's 0. because current's 0. And then at the next segment, it's going to start negative, and then it's going to go to 0 at time t3. What's the maximum negative value? Well, we take V0 and M3. And so what we're going to see here is negative V0 squared and then T3 minus T2. So I don't have any numbers here, but you could plug in numbers if you wanted. So just a thing to point out here. Since power is greater than 0 here, this is power delivered to the capacitor. And here, power is negative, so this is power supplied by a capacitor. And then we can do the work, right? So the work at any time t is going to be the integral over p for all times less than t. So let's just write that out. And geometrically, right, this is just the area under the curve, left of t, if you want to be more specific about it. So we can sketch this, put in our important times again. Well, assuming that it's 0 energy stored at time 0, we're going to have 0 energy stored at time 0. Then we start this linear increase in power. So what that means is as time moves rightward, we're adding to the area under the curve. So it's going to increase quadratically. And so what is that? Well, it's going to be the area under this curve. What's that area? Well, it's 1/2 base times height. So, oh, and I think I forgot something here. I need a C here. There needs to be a C and a C. And so this needs to be a C. We need a C here. Okay, anyway, this area, right, this is T1. So the base is T1. The height is C V naught squared T1. So when I take the area 1/2 base times height, well, I get 1/2 CV0 squared. And that makes sense given the formula we calculated above, 1/2 CV. Okay, so there's that. Now, as we continue the integration rightward for times T1 to T2, well, P of T adds nothing to the integral. So our energy storage remains constant over that interval. And then in the remaining part, it's going to decrease like this until it's back down to 0 energy stored. Again, because the voltage goes down to 0, and because of this equation up here, well, we know that the power discharges this thing, so that the work has to go back down to 0. Okay, so I've shown you how current, voltage, and power are related in a capacitor. We plotted here, right? So you can see here that the current is proportional by this capacitance to the slope of the voltage as a function of time. And then power is just the product of those two. And then the energy stored, so W, is the integral of the power. So it has the interpretation of being the area under the curve of the power. Additionally, one thing we'll point out is that the voltage cannot change abruptly, although the current can change abruptly, and you see that happen here. But because the voltage up here is a integral over time, it can't change abruptly, although the current can. Okay, well, we'll end it there. Thanks for watching. Leave a comment, like, subscribe. Thanks.